Hi, my name is Kevin Tubbs, and I'm the Senior Vice President of the Strategic Solutions Group at Penguin Computing. Today, I'll be talking to you about expanding your vision of what is possible with end to end solutions for HPC, AI and analytics, cloud, and data technologies. I'll start with talking about Penguin Computing and our mission. We are truly trying to expand the world's vision of what's possible. And we do this by engaging with our customers and trying to understand their most challenging problems and then delivering the right capabilities to increase their business objectives. We want to take the technology challenges and problems off the table. And that gives us our mission. At the end of the day, we want to provide an unprecedented customer experience. Today, I'll be walking through the agenda, talking about the prevailing markets, trends, and we're seeing today in HPC and AI, how we're addressing those market challenges with our technology practices. And then I'll go into our overview of our workload optimized architectures, and then deep dive into some of the solution examples. So, what we're seeing in the market today is this move toward customers being more interested in how to get their workloads accelerated, how to use technology to gain time to value and business insight. And inside of those, we're seeing this layer of hardware abstraction where customers are retreating from understanding the infrastructure into focusing on the application space and the workloads that I need. With the complexing changes in emerging technologies, this becomes very hard to keep up with. And that leads us to the platform complexity. The need to address different technologies to find different workloads that we're seeing in heterogeneous computing. And we really believe that the only way to address that in a way that delivers capabilities is to focus on software defined architectures. It's also becoming a challenge to manage at each level these different expertise as the hardware gets specialized. Another aspect that we're looking at is Cloud 2.0. What we're seeing here is how the cloud is being used to deliver those technical and business objectives. We're coming out of the cloud first initiatives where we're trying to push everything to cloud. And we're also seeing that even within cloud providers, that we have different options of capabilities. And the key thing is trying to understand and move your workload where it is appropriate. So we think cloud appropriate. And for here, this also includes both hybrid and multi cloud to be keys to delivering capabilities for success. And finally, one of those aspects is also flexible usage models. Once we've identified a technology and attempting to deliver that complete end to end solution, where it actually sits and what business vehicles we use to deliver it really is up to the customer. So we want to have a flexible usage model that allows us to deliver on premises in traditional ways, private cloud, public cloud, or all the way up through as a service. But the main key here is it's designed to cater to the customer's workloads. So, how we're addressing these market challenges that we're seeing, that we focus on four key technologies areas: the high performance computing technologies, which we've had a long tradition in serving, AI and analytics technologies, which over the past 3 to 5 years, we've had a tremendous growth in serving as well. The data technologies, which is an abstraction just up from the storage, is very important to delivering workload optimized architectures. A lot of the workloads in HPC and AI are becoming more data driven, and we're seeing the growth of data inside of organizations be very exponential. And then last is our cloud technologies practice, which focuses on how to deliver workload portability, understanding the infrastructure and workflow management tools that allow you to run that workload where it's most appropriate. So we try to look at all of this to take these advanced technologies, package them together, deliver them in a way that enables the customers and organizations to focus on what's truly important, their business insight and their time to value. So now I'll jump into our workload optimized architectures. Based on the four key technology practice areas that we've discussed, we're looking at how we build modular reference architectures that are able to be used and combined to address technical compute problems within our customers' organization. And we believe that addressing on these key areas allow us to solve the problem holistically and deliver a complete environment. And we'll go into that in more details in some of the later slides, and I'll also give some examples. But here within each practice, we have different layers of capabilities and technologies that address key points. So, for instance, the data practice, we're looking at some of the trends we have in persistent memory and the tier of data and performance required in big memory. We're also looking at active data, which talks about flash storage, and also trying to address the growing need to have data lifecycle management and keeping data for longer periods of time, and also managing the growth of sensor data, different types of machine generated data, and that allows us to have capacity storage. If you go over to the cloud practice, our cloud base focuses on how to deliver workload portability, all the way through how to deliver multi cloud workflows, and also, especially with lately, our work from home capabilities, how to enable researchers, designers, and end users to do those workflows from home or from anywhere truly. And then as we move over to the HPC and AI and analytics practices, we're looking at just how do you enable HPC in the context or way that's important to your environment, also wherever it is for AI. So we look at edge analytics, also data center analytics, and then we also look at edge to core. But if you look at all of these together, it's how do I have a reference architecture that's engineered, vetted, and tested with the right hardware that's optimized. And then on top of all that, we're going to layer in the software layer, which can be third party software defined architectures, specialized in the different technologies in the practice, also open source software, and even proprietary software built and designed by Penguin that allows you to deliver this in a cohesive and manageable manner. And then on top of that, we have the services organization, which we use to make sure that we can design a safe architecture, cater to the customer specific needs. We offer professional services to do that, integration and one off type of work with the customer, all the way through managed services, which is completely ongoing, and all the way through hosting services, where we host this technology in a data center or colo for you. And then all of those, once we solve that problem, once we design a holistic approach, how do we deliver that to the end customer? And that can be on premises traditionally, um, which also can include a private cloud. You can do that in public cloud. What we're seeing a nice trend or towards is hybrid and multi cloud. And ultimately, we can also deliver that on premise as a service, where we take all of that technology and deliver it as an OpEx. So that's our overview of our workload optimized architectures, and I'll jump into some examples. So first, I'll start with active data. Active data is our reference architecture for flash storage. It's aimed at having a complete turnkey, high performance file system or storage solution that's highly scalable, and key thing being easy to deploy, configure, and manage. Also, we want to be able to expand that whenever the customer needs. The main goal here is that there's a flexibility and it's leveraging flash technology. This specific example is our active data with Weka IO, Weka FS, and I'll go into some more details. So one of the key things that we provide in all of our reference architecture is a common holistic approach to start with the customer's workload and application layer, understand which applications you're using, how does that affect your business and technology objectives. And from there, it's going to give us some technical requirements. Do we have to only focus on HPC workloads, analytics and machine learning, or AI, or some combination of all of that? Once we understand that, we are also going to have to understand how those technologies are delivered to the end user. So we have a layer of software technologies that we have to understand how to deploy and set up. And even for a storage solution that understands and leads us to the types of technologies we need to support. And then once we understand that, we look at the compute technologies. What type of specialized compute and networking is required to deliver those performance goals? We're getting to the age of accelerated computing with different types of accelerators like GPUs or very dense CPU clusters that are scale out and large scale. So as we understand that, that's going to understand the IO and data demands on the data layer. And that leads us to active data with WECFS, where that's our choice for the data technologies. And we'll go into some details of why we think that that's important. And then once you have those components, we also need to understand where is it being deployed, how is it being built and designed efficiently into your data center, or efficiently into a cloud platform, or into one of our hosted data centers. And then once we have all of those components together, we look at what Penguin Computing services are required to help the customer deliver this efficiently and reduce the time to stand up that capability, which reduces the time to value for the customer. So this is another example of one of the reference architecture solutions. And we're able to scale that out to different performance requirements and capacity requirements. This example would be a 40 node active data rack with WECFS. It has up to about 7 petabytes raw and close to 6 petabytes usable. And we're using a 16+2 erasure coding. We're also able to get the max and nominal power so we can plan the infrastructure correctly. And we have a vetted and tested and benchmark estimate of what the performance is. And the key things with WECFS is that it is a very performant file system shown to have linear scaling and capabilities. So we look on the left, we're looking at read performance for a single GPU client, where we're able to get above 10 gigabytes per second. And the key things here is that by using a WECFS file system, we're able to do better than local SSD performance, as well as much more performance than all flash NAS type of solutions, which rely on NFS. And the other key thing to note here is we've also tested this on scaling from multiple DGX clusters or large GPU clusters. So how you have an individual node performance capability and also testing the ability to scale that over multiple nodes and getting favorable scaling. So next, I'll give a last example of one of our solutions. We're launching 7 solutions this week, so please stay tuned and check out the rest of the website as well as Penguin Computing if you want to learn more about them. In this case, we're going to present a reference architecture, but also give a case study on AI ML inferencing. Our live data solution comes in partnership with Memverge Memory Machine and is focused on big memory computing. Here we're looking at solving the problem when data is greater than memory and how using persistent memory technology can bring the data closer to the compute infrastructure and operate at memory speeds. And we'll see later on that we use this to accelerate workflows, but also increase TCO by having cost reductions. And then overall, going to deliver a better inferencing experience for the workload. Generally, this applies to real-time workloads, memory-centric, low latency. You can also think about in-memory computing for databases. These types of technologies would leverage live data to improve the overall performance, but also the productivity. So here again, we're looking at the Penguin Computing approach to building a complete environment, a holistic approach to solving the problem, looking at the different workloads running through the software. And here we're just focusing specifically on the data technology, in this case, memory speed computing. So we're actually delivering food memory lakes using Memverge as a software-defined architecture to provide the pooling and aggregation of persistent memory and DRAM. So if we look here, this is an example of how to scale out and use live data with multi-nodes. We have a specific workloads. In this case, things you want to focus on with the real-time, low latency workloads are trading data, in-memory analytics, machine learning and AI. Also HPC with burst buffer technology, life sciences, anytime you need fast in-memory checkpointing. And we also have some VDI applications that are very interesting for M&E, where persistent memory and memory pooling or memory lakes give you the capability to solve problems a lot faster, but also have increased productivity with data services added on top of memory speed technology. Combining DRAM and persistent memory in a approach with a software-defined architecture from Memverge allows you to recover from crashes, be able to work on larger data sets, which really helps the creative artists deliver their end result. And if they can do it fast and having protection for productivity, it allows them to iterate on their design faster and get more time to iterate on that design, which ultimately is their goal to deliver the right creative product to their end customer. Basically, we're looking at the different components where we're having the software defined architecture provide a transparent memory service. And the key thing there is you're able to deliver persistent memory and DRAM without changing your code. If you do have a situation where you actually need to optimize and design it yourself, there's also an SDK. And then there's the distributed persistent memory engine that allows you to add data technology services on top of non volatile memory. And then under that is how we use RDMA transport as well as a cluster manager to pool this into memory lakes. So I'll go into some case studies. So we'll start looking at a use case, how to use live data for big memory applied to AI and ML inferencing. So here the problem. When data is greater than the size of DRAM, AI and ML workloads begin to slow down dramatically. Another problem is memory intensive inferencing jobs take a long time to load and restart. So if you have an inferencing workflow that you want to change different models online in real time, this allows you to make changes to the model, understand what's going on, but also roll back. These are common problems you may see in production inferencing. What's the solution? So to do that, live data allows you to create big memory lakes that consist of both DRAM and persistent memory, and also scale across multiple nodes. This allows the capacity for all the data to fit into memory speed technology. So you can actually run the model and the embedded tables that support the model in persistent memory or in memory speed technology. In other cases, when you don't have that, that the size of the models grow with scale and the number of inferencing models you're using in production, as well as the amount of embedded data that goes with that. And as those scale and get larger than what's in your DRAM, that's causing you to have to use NVMe technology or swap, which is very fast, but still orders of magnitude of latency issue. So here, this is when real time and latency is important. The other solution would be using data services provided by Memverge, Memory Machine, and Live Data to have faster data recovery as well as online restarting and changing of models. So that's the solution provided by Live Data. So if we look at this applied to a AI ML inferencing workload, here we're just going to give some high level summary of the results. But if you want to learn more about it, please reach out to Penguin Computing and Memverge. We have a full white paper on this and talk about it another time. Here, what we're looking at the total inferencing time when using DRAM only, DRAM and persistent memory, or all of it is sitting in persistent memory, and when the problem has to use DRAM and NVMe technology for swap. What you see here is we have our baseline as the performance if you're running in DRAM. We all know that if I'm running in DRAM and my model fits, I'm going to have great performance. What we also show is for that same model size, if I use DRAM and persistent memory, I'm able to be, it slows down a little bit, but still on par with the DRAM only performance. And then there's opportunities where I can put the both the model and the embedded data in persistent memory. And then with that being the case, it's a little bit slower, but still on the same order. But in the case that as I scale the different problem sizes of the model and the embedded data, and that data gets greater than the DRAM, and I have to start using swap, we see on the end, when I'm using NVMe in that case, I have a drastically slower total inferencing time. And this is the overall takeaway of how understanding the combination of the specialized compute and operating in memory speed can drastically improve your overall workflow. In this case, not shown on here, but we have more data. We were able to observe up to 4x transactions per second, up to 100x lower latency. And then here's also the TCO of combining persistent memory with DRAM instead of increasing the complete size of DRAM in the cluster to address this. That also allows us to have 50% cost savings over DRAM for these specific workloads and these configurations. So what you have here in summary is a way to decrease your overall inferencing time, increase in productivity. So that completes my overview into how we're expanding the world's vision of what is possible using our software defined architectures combined with key hardware, combined with our services and expertise. So please feel free to reach out to Penguin Computing if you have any questions, and I thank you for listening to us.